Last day we talked about separable differential equations, learned how to solve them, and did an application. I want to do another application today, which is somewhat involved. It's from the exercises. Exercise 59B, and we are in section, as before, section 15.2. So let me explain the details of what this exercise says. It says, we have a chemical A and we have a chemical B, and when they come together, they make chemical C. In such a way that 2 grams of this one combine with 1 gram of that one to make 3 grams of this one. Originally, we start with 20 grams of this one and 5 grams of this one. And the objective of the exercise is to find how much C there is in the mixture as a function of time t. Got the idea? Right? So let's let x of t be number of grams. Don't say amount. Lots of people say let x be the amount of C. Since I've given you units here, these were all grams, then I think you should specify the units of C of t that way as well. Grams of C of t. And I didn't want to use the letter C because invariably I'm going to get a constant integration here, which I like to call C, so I'm trying to stay away from that letter. So let the number of grams of C in mixture as a function of time t. Now, there's something in this problem. Right now, you can't solve that problem. You do not have enough information. But what often happens in chemistry is the following statement, that the rate of change of the amount of C is proportional to the amounts of A and B. That if you've got lots of A and lots of B, then C will form rather quickly. But if you don't have a lot of these, and at some point in here, B is going to start to run out before A does, and you get down to teensy-weensy amounts of B, then C should not be formed so quickly. So the text says that the rate of change in the amount of C is proportional to the amounts of A and B. It left out one key word that I want you to discover. So if we started to model, we would say, well, dx dt is the rate of change in the amount of C. And it says it is proportional to, so we would throw in a k, to the amounts of A and B. Now the question is, what are we going to write? The crux of the problem is right now, getting that right. Now, if I were teaching you in person, somebody would come up with a suggestion, A plus B. But if you think about that, it can't be right. Think about it. We realize that B is going to be used up first, because it's going to be a ratio of 2 to 1, right? When you've used all this up, then you'll have 10 up of the A, and there'll be 10 left of the A. If this were true, when the B is gone, you would have this, and it would say that the x dt is still positive, it's still being made. And that can't be true. So it can't be a plus sign. So what's the alternative? Well, a natural alternative is to be that. Now if B runs out, dx dt will be 0. And that will make sense. So I think the key word that was left out is not the amounts of, but the product of the amounts of was the missing word. All right, now what does this mean? This means amount of A left, agreed? And this is the amount of B left. That's what it said. The rate of change of C is proportional to the product of the amount of A and B there, which means left. Now the objective is to find x as a function of t. That means this has to go and this has to go. And that's your next hurdle then, is what are you going to do about A if A here means the amount of A that's left? Well, think about it. You started with 20, and then you used some of it up. Now the question is, what are you going to write for what's used up, right? So this is supposed to represent what's left. This is the original, so you're going to say minus what you used up. Well, think about this. If you've got X grams of C, where did it come from? It came from AB. How much of it came from A? Didn't 2/3 of this come from A? So what you used up is 2/3 of it. That's how much A you used up in producing this amount. And similarly, B is going to be original minus how much did you use up? X over 3. Because again, 2 and 1 giving 3. So that's what we can put in. So dx dt now then is equal to k 20 minus 2x over 3 and 5 minus x over 3. Along with the initial condition that will start our clocks when A and B are brought together. So again, we've got an initial value problem to solve for x. More difficult than the previous ones, as we're going to see. All right. So how be we do the following? I hate these fractions. Would it be okay with you if I brought these two to a common denominator? I brought these two to a common denominator. I pulled that 3 out. I pulled that 3 out. And I have a 2 and a 20, and I pull out a 2. So see if I can get that right. So we'll have k over 9, pulling out the 2, 10 minus x. No, not, because we're bringing a common denominator. That's going to turn into a 60. Then I pull out the 2, 30. And then here, 15 minus x. How does that look? I pull out the 2 3's after I brought it to common denominator, 60 minus and 15 minus. All right? All right. So we got to solve this differential equation. Again, we only have one technique at the moment, and that is separable. And this baby is separable. I don't want to carry this around. Do you mind if we give this a new letter? How about we call that L, okay? Just so it's not so cumbersome. So 2k over 9, we will denote by L. So we can separate it into dx over 30 minus x, and 15 minus x is equal to L dt. How's that? Right? So this down to the bottom, the dt up, and leave the L up there. So we separate. We can now say the phrase that Trim likes, a one-parameter family of solutions is defined implicitly by writing integral dx over 30 minus x, 15 minus x is equal to integral L dt plus constant of integration c. Happy with that? Integration to the right trivial. What about the left? First year problem, how do you integrate that? Answer, partial fractions. So we're going to partial fraction, that integrand, something over, how do we do the following? Not necessary, but let's, I hate minus signs in front of us. It would be okay if I wrote that as x minus 30 and x minus 15. That same thing. Multiplying both of them by minus 1, which changes nothing, right? So then we'll have x minus 30 here, and we'll have x minus 15 here, and we will need the numerators, dx, and on the right-hand side we get LT plus C. We talked about this not too long ago when we were doing Maclaurin series. We had the same kind of scenario of finding a partial fraction of something that looks like that. And remember what I said was that if you've got non-repeated linear factors, there's a fast way to get the numerator here and here without going through that official technique from first year. You want to know what goes on top of x minus 30? You cover it. And you put 30 into what's left. Putting 30 into here, 1, putting 30 into here, 1 over 15. 1 over 15. You want to know what goes on top of x minus 15? You put your hand over and you put 15 into here. You can get 1 over minus 15, minus 1 over 15. Let's check. Then this one times this one plus this one times this one had better give me 1. That one times that one gives me those x's and those x's, they cancel. This one times this one gives me what? 2. Right? This one times this one gives me 1, 2 minus 1. What? Looks good, right? There's our partial fraction decomposition, and we can now proceed to integrate 1 over 50, the logarithm, x minus 30, minus 1 over 50, the logarithm of x minus 50 is equal to LT plus C. Question: do I need the absolute values? First year calculus says, put them in. First year calculus says so. It says, in case this is negative, in case that is negative. Are they? Can they? And the answer is yes, okay? Definitely, because x is going to start at 0. In fact, this is always going to be negative, right? And what's the largest value that x can be? If we start with 5, all right, and it's a ratio of 1 to 2, is not the maximum amount of c going to be 15. So again then, this is always going to be negative, so it's a good thing that we put the absolute values in. Now I want to say, what we said here, a one-parameter family solution defined by. All right? Now I got a choice. I do want my solution explicitly. I got a choice of solving explicitly now and getting the constant later, or getting the constant now and solving later. In my opinion, usually it is beneficial to solve first and get the constant later. Just from my experience, that turns out to be easier. So let's solve first. So first thing to solve, I think I would multiply by 15 and then bring the logarithms together. So the 15 up there equals 15 LT and 15 C. The logarithms, so that's gone and that's gone. The log of somebody minus the log of somebody is the log of this guy divided by that guy. So we could write the logarithm of the absolute value of x minus 13 over x minus 15. Now to me, I really don't need the absolute values now, because that's negative, this is positive, but I'll leave it there anyway. Next, let's exponentiate to kill off the logs. X minus 13 over x minus 15 is equal to e to the 15 LT plus 15 C. Let's get rid of the absolute values. X minus 13 over x minus 15 is plus or minus. And I'm going to write e to the 15c times e to the 15 LT. And then I'm going to say to myself, this is just one great big fat ugly constant. Why don't we call that d? d e to the 15 LT. We're getting there. Now I'm going to propose that we take this and we put it up there. X minus 15. And now I'm going to propose that we take anything that's got x's in it, bring it to the left, and anything with no x's in it, take it to the right. So there's that x there. That's that guy. U to the other side. No x's. On this side, we have this one times that one. That's got x's. So minus x d e to the 15 lt. And then this one times this one, you're staying minus 15 d e to the 15 lt. Let's factor out the x. 1 minus d e to the 15 lt. And then let's divide it by this. So x of t then is equal to 30 minus 15d e to the 15 lt over 1 minus d e to the 15 lt. There, we've got the amount of c explicitly now. Now let's go get the d. We've got that x at 0 is 0. So if we put in t is equal to 0, we get 30 minus 15d over 1 minus d. Putting in t equal to 0. Well, if that's true, then the top has to be 0, and that implies that d is equal to 2. So finally, x of t is equal to 30 minus 15 times d, that's another 30, e to the 15 lt, over 1 minus 2, e to the 15 lt. Grams. There then is the amount of c in this mixture as a function of time t. I'm going to rewrite it to make the next discussion a little bit more obvious. Suppose I multiply top and bottom by e to the minus 15 lt, right? Just multiply top and bottom, right? If I do that, right, in addition, let's multiply by, let's do minus, right? So what happens? This guy becomes minus 30 e to the minus 15 lt. Multiply. This guy becomes, that cancels that, and we get 30. On the bottom, this guy becomes minus e to the minus 15 lt. And this guy here becomes, I'm multiplying, the exponentials cancel, 2. That's just a rewrite, but it helps me discuss something in a second, all right? Now remember what L was. L was equal to 2k over 9, as I recollect. So I can put that in there, but I don't want to bother at the moment. Well, I think what I'd also like to do, notice there's a 30 and a 30. Maybe I'd pull that out and write 1 minus that. There. 1 minus. There then it is. Now I'd like to ask a couple questions here. Suppose you were to draw that graph. Suppose I asked you now to draw me a graph of this function. Now, one way would be go back to first year, talk about critical points and mountains and mins and all that stuff. But we don't have to do that. We are intelligent. T and x of t. You know that it starts at 0. Let's check that out. If you plug in t equal to 0, you better get 0. If you put in t equal to 0 here, this becomes 1 minus 1. Yeah, good. All right, that's good. All right. So it starts there. Now, what's going to happen in the long term? Physically, we saw that back here. As time progresses, the A and the B are going to make the C, and since they come together in a 2-to-1 ratio, the B is going to be used up first, and when you use up 5 B's, you will have used up 10 A's and produce, therefore, 15 C's. Does our function predict that? If we let time get huge, what happens to that? It's gone. Because L is this, and K was positive. So this is going to go to 0. That's going to go to 0. You're going to get 30 over 2. 15. Looking good. So that means up here, that it never gets above that. So our mathematics is confirming what we could see physically. Now in between, do you think it could look something like this? And the answer is, not really. That would be idiotic. Okay? We say, hey, look at the C growing, and then suddenly, oh, C's turning back into A and B. Well, that's ridiculous, okay? Right? Don't you feel that it has to look exactly like that? That it has to look like that. That C will get bigger and bigger and bigger, all right, but it will gradually level off at 15. That must be a picture of that. Now, I leave you, if you want, to confirm that. It's saying no maxes or mins. You want maxes or mins of this thing? You set the derivative equal to 0, you try and solve. You should be able to solve no solutions. If you want to know it's got this shape, you say it's concave down, go find yourself the second derivative of this. Be my guess. And show that it is always negative. Physically, we can see that it has to look like this. And that mathematics has a better idea of for you to say, take your calculator, computer, and say, draw me! And see. Put in an L. Put in L is equal to 1. It doesn't matter what it is. And say, draw me, and you'll have to see a picture that looks like that. So there's a rather involved example of separation. Right? Separation was only a minor part of it. It was getting it set up that was difficult, and then playing with the solution after we did the integration. But it is trying to get us used to mathematical modeling. Mathematical modeling is not like other parts of mathematics. I can teach you to do partial fractions in a day. I can teach you the product rule for differentiation in a day. I do not teach you mathematical modeling in a day. I give you the ideas, and the more and more and more you do of it, you get better and better and better and better. But it's not something you become an expert at in one day. Realize that. It's going to take practice, and there's lots of exercises with these applications for you to get used to this process. Next section is 15.3. There's many different ways to solve first-order differential equation. I probably know of about 10 ways. But the vast majority of first-order differential equations that you see in applications fall into two categories. One, separable, and two, what we'll talk about in 15.3 called linear first order. So that's all we're going to cover in the course, is those two methods for first orders. You'll find a couple of other methods embedded in the exercises. One called homogeneous and one called Bernoulli equations. You'll see those in the exercises, right? But I don't hold you responsible for those. But you need to know these two, because again, the vast majority of applications use these types. So if you happen to run into an application that uses another type, then you have to go look up that type. So what we want to talk about are linear first order. Differential equations are, or can, are those that can be expressed in the form this dy dx plus p of x times y is equal to q of x. Now remember, last day I told you we were considering differential equations that could be written this way. And last day we talked about separable ones, and that means the f had to have a special form. For linear first order, you're saying that f guy must be this minus that. Now, I'm not going to tell you why it's called linear, because we're going to study linear differential equations of any order in huge detail later, and I'll tell you why we call them linear then. Right? So right now, linear simply means you can write it in this form. And I've got an example to illustrate the idea of how we solve all of them. Consider this example. That dy dx plus 2y over x is equal to x. That's clearly of this form. I won't always give you a differential equation. In fact, I should give you this. Right? If I gave you that differential equation, it is not in this form. So I'm going to take it back, right? I'm going to put it into that form that I had a minute ago. But you might have to do that in practice. Now, I give you this and I ask you, the idea of a differential equation is to get rid of the derivatives. We saw how to do that when we did separate ones. I ask you, could you integrate this term? The answer is yes. The antiderivative of this is y. Could you integrate this? Yes. X squared over 2. Could you integrate this? And the answer is no. Don't say to me 2y log x. Because if you do that, I'm going to shoot you. Because remember, the objective here is to find y as a function of x. So y is not a constant. So don't just integrate the 2 over x and say 2 log x. So you can't do that. All right? But suppose I come up with an ingenious idea, and before the class is over, I'll show you where I got it, of multiplying by x squared. Multiply everything by x squared. So we will have x squared dy dx plus 2xy is equal to x cubed. Right? Multiplied everything by x squared. Now I ask you the question again. Could you integrate this? The answer is no. You made it more complicated. Could you integrate this? No. It's complicated. Could I integrate that? Yes. Okay. I went from 2 I can integrate down to only 1 I can integrate. But the problem is, you're looking at this piecemeal. Don't look at it individually. Think of them as a pair. And when you see a plus sign, that should automatically draw you to the product rule. So could you think of a product to put in here so that when I differentiate it, I would get both of these? And the answer is, well, obviously the product has to be, because the product was just 1 times the other plus the other times the derivative of 1. If this is to be one of them, then that product has to be x squared y, because that will give this one. This one times the derivative of that one. But what about the other? Is this one times the derivative of that one? The answer is yes. All right? So we've written the differential equation this way. We can say, now we could integrate x squared y is equal to x to the 4th over 4 plus c, and I can even solve for y. Y is equal to x squared over 4 plus c over x squared. And we did it. So for that example, the key was discovering what I could multiply this thing by so that the left-hand side would collapse to the derivative of a product. And that's how we solve all. That's how we solve every linear first order. All I have to do is show you how to get that guy. So I'm opposed to do that now. But that's the idea for finding solutions of all linear first orders. So let's say, if we multiply this by some function mu of x, and I don't want it to ever be 0 because I don't want to multiply by 0. So the objective is to find this function. In that example, this was x squared. But now I'm trying to find out what that guy has to be for any first order differential equation whatsoever. So then we would have mu dy dx plus mu p y is equal to mu q. So I'll drop all the of x's just so it doesn't look so cumbersome. And what did we want to happen? We want left side to be derivative of a product d product equal to mu dy dx plus mu py. And the product, right? If we're thinking about that again, this is going to be the product rule for what's inside there. Well, if this is to be one of the terms in the product rule, doesn't that product have to be that? Right? Okay? Right? So we want this to be true. We want to put this product in here so that when we differentiate it, we get this. Right now we're getting this, we don't know about that. All right? So you want that to happen. Right? And what's that supposed to be equal to? That's supposed to be equal to mu q. All right? So you want the left-hand side be the derivative of the product, and that's going to be the mu q. All right? All right. So let's look at this. Let's look at this. So we want this thing to be equal to this thing. Let's do the product rule. We would have mu dy dx plus y d mu dx must be equal to mu dy dx plus mu py. Our mu guy that we're looking for must satisfy this. Well, looking at it, oh, you'll notice that this one cancels that one. Oh, this cancels that. So what do we got? That d mu dx must be equal to mu p. So if we're looking for the mu function, it's got to satisfy that. But what's that? That's a differential equation. In other words, we've gone from solving this differential equation for y as a subproblem in order to get this stuff to happen. That mu must satisfy that. But what kind of a differential equation is that? That's first order, and it's separable. We could write that d mu over mu is equal to p times dx. And therefore solutions are integrating the logarithm of the absolute value of mu is equal to the integral of p of x dx plus c. Right? Now, what am I searching for? I'm searching for a function that will accomplish what I want. I don't want them all. One is I'm happy with. So let's not write solutions. Let's write a solution is, and drop off the c. Say, there's one. And now let's solve for mu. Solve for mu, the absolute value of mu is equal to e to the integral of p of x dx. So mu of x is plus or minus e to the integral of p of x dx. And because I want one, I'll choose the positive one. And notice, I said back here, I want to multiply by a function which is greater than 0, and indeed, that guy is always greater than 0. So that's excellent. So where are we now? We're saying, if you take this differential equation and you multiply it by that thing, ugly as it is, the left-hand side will turn out to be the derivative product. So we're going to put that mu here, we're going to put that mu here, we're going to put that mu here, and we're going to look at it and make sure that that happens. So let's take this thing and put it there. So we will have e integral p p of x dx multiplying dy dx plus e integral p of x dx multiplying p and y equal to q e integral p of x dx. There I'm done. I simply replaced all these mu's by that thing. Now the claim is, if we've done this right, that the left-hand side is the derivative of a product. Let's make sure. So what's going to go in here? Well, my claim is what has to go in here is this. Because if I take this one times the derivative of that one, I get that one. The check is this one times the derivative of that one equal to that one. So there's the y. If you differentiate this, the derivative of e to the anything is e to the anything times the derivative of that anything, that's p. Yes! All right? It works. And now we can simply say integrate. So on this side we got p of x dx. And so we say integrating with respect to x, that y, e, integral p of x dx is equal to integral q of x, e, integral p of x dx. And then let's throw dx, and let's throw on now our constant of integration. And we can even solve. We can take this over and say solution is explicitly y of x is equal to e minus integral p of x dx integral q e integral p of x dx plus c e minus integral p of x dx. I simply divide everything, both things on this side, by that. All right? There it is. I've got you, if you like, a formula. If you're given a differential equation that's written this form, you can say, there is a formula for the answer. I do not recommend that you memorize formulas. What I recommend here is that you remember this, that mu is equal to that. That's what you remember. That the mu function is that. That's not so hard to memorize, all right, as opposed to this. This thing is called an integrating factor. Integrating a factor because we're multiplying by it. Integrating because if you do multiply this differential equation by that integrating factor, then the left-hand side will become a derivative of a product, and you integrate and you solve. That, to me, is what you should remember. That thing, all right? The key is make sure that the differential equation is in this form, right? So let us, as an example, go back to that introductory one that I had and show that I can get that integrating factor that we saw. Remember what I had was x dy dx plus 2y was equal to x squared. That was the way it originally started. I said, first thing I was going to write in the required in that form, and it is necessary. Dy dx plus 2 over xy is equal to x. There. It's now in this form. And so we can say an integrating factor is formula e to the integral of the p guy, which is 2 over x dx. And if this is a negative sign, make sure that negative sign gets in here too. P is everything that sits in front of this y, Clear? And the integral here, you can do that. This says e to the 2 be logarithm of the absolute value of x. And we do not include a constant integration. All we're wanting is one mu that works, so we don't include integration constants. Simplify it. And make sure you know how to do this. I've seen people fall into this. Can I put that 2 right there? Right? And e to the log of anything is the anything. So there it is. Simplify. That's our integrating factor. Which means I'm supposed to take this and multiply it by that. All right? Now, I really here could dispense with the absolute values. Agreed? Because it's a square, I could eliminate them. I'm not going to, because I want to point out, suppose this were, and I should have made it, suppose that were a 3. Let me go back to it, okay? Change this to 3. Change this to 3. Change this to 3. Change this to 3. And change that to 3. It's not going back to my original example, but it's worth doing this to make a point. So now what I'm supposed to do, I'm supposed to take that, and I'm supposed to put it here, I'm supposed to put it here, and I'm supposed to put it here. Right? But then I'm supposed to talk about integration. Does anybody like integrating absolute values? The answer definitely is no, neither do I. But let's take a look at it. If x were greater than 0, then I would throw away the absolute values. Agreed? I would just dispense with them, and I would be looking at then x cubed dy dx plus x cubed times that 3x squared y is equal to x cubed times that one, x to the 4th. Right? So if x is positive, I throw in the absolute values, I got x cubed, and I put it here, I put it here, and I put it there. And we know that the left-hand side is going to be the derivative product. But what if x is less than 0? If x is less than 0, do you agree you would replace this by minus x cubed? Or if you like, minus an x cubed. And what do? You put that. You put it here, you put it here, you put it here. So you get minus x cubed dy dx. You get minus 3x squared y, and you get minus x to the 4th. And now compare that to that. They're the same thing. Now all those are minus, throw away the minus sign. So whether x is positive or whether x is negative, we get to this one here, and we only have to deal with it, right? That's going to happen anytime you have something here like this with an odd power. You can see that's going to happen, right? It doesn't matter whether you look at the positives or the negatives, you're going to look at the same differential equation. So now we can carry on. D by dx, we know that the left-hand side is a derivative of our product. And you can say, I know it's going to be x cubed and y. It's going to be coming from here. What I highly recommend, because I've seen so many people, is really check your integrating factor by saying, in addition, that one times the derivative of this one must be that one, and indeed it is. Right? Indeed it is. Make sure you do that check. In fact, I usually warn people, if you get that integrating factor wrong, and you do not check it here, I will look no further in your solution. If you don't have the smarts to take 1 second to check that this times the derivative of this is that, I'm not very sympathetic with you, and I won't look any further. So make sure you check. Make sure what you're checking is that what you did over here was correct. All right, and what's on this side is x to the 4th. So we integrate with respect to x, and we get x cubed y is equal to x to the 5th over 5 plus c, and therefore y of x is equal to x squared over 5 plus c over x cubed. And there's our solution. There's our one parameter family of solutions. Is it general? You don't know. I do know that that's general. And we will prove that next day, right? Next day. So there's one example. We'll do some more examples next day of these linear first order ones. And I'll get around to talking about that when you find a one parameter family of solutions of a linear first order, you're guaranteed it's general. That is, this is all the solutions. There cannot be any singular solutions.